little red dot.
Okay, welcome again, and for our next speaker, and for the last session today, I'm pleased to introduce you Vincenzo Antonelli from Politecnico di Torino, and he will speak about Ulrich bundles on Hirzebruch surfaces. Thank you.
Okay, so thank you very much for this opportunity. I would have loved to be there in Campinas, but I hope that after this whole pandemic thing is over, there will be another chance. So as you can see from the title, I will talk about Ulrich bundles on some kind of surfaces, and these surfaces are the Hirzebruch ones. So let me just fix the notation and the general setting. PM will just denote the projective event space, and we will work over an algebraically closed field of characteristic 0. You can just think of the complex numbers from now on. And a variety X will be just a smooth closed integral subscheme of this projective space of dimension n. And typically we will denote by hx and kx the hyperplane class and the canonical class. So the hyperplane class is important because we will consider embedded varieties. So as we will see in just a moment, the notion of being Ulrich is strictly related to the embedding of the variety inside the projective space. So this will be important. And a vector bundle will just be a locally free sheaf of constant rank. So one of the main character will be the Ulrich bundles. The other will be the Hirzebruch surfaces. So we will focus on an infinite family of surfaces. And but for now, let's just say something about Ulrich bundles. So I'm the first one to explicitly talk about Ulrich bundles, but I won't be the last. So I'll do the honors to introduce them. But I will not say anything so then I don't spoil the surprise of the other talks. So by the end of the week, the idea is that you have a full picture of Ulrich bundles. If we take a coherent sheaf over a variety, it's called ACM, so arithmetically Cohen-Macaulay. If it's locally Cohen-Macaulay and it has no intermediate cohomology. By no intermediate cohomology, I mean that if you take the coherent sheaf E and you twist it by multiple of the hyperplane section, you can only have H0 and Hm, where n is the dimension of the variety. And why we are interested in ACM sheaves? Well, in some sense, the families of ACM sheaves supported on a variety gives us a measure of the complexity of the variety. And one can think of the famous Ulrich's theorem over the projective space, which basically tell you that the ACM vector bundles on the projective space of dimension greater or equal than 2 are the vector bundles which are direct sum of line bundles. So the basic idea is that simple varieties should support simple category of ACM sheaves. Here I'm using the word simple, but it's not the simple used in algebraic geometry. We will see that in a few slides. Ulrich bundles are a particular kind of ACM bundles. They have the additional property of having maximal number of generators. So if you take the module of global sections, it has the maximal possible number of generators, which is the rank of the vector bundles times the degree of the variety. And actually, just an historic note, they were introduced in a purely algebraic context in the '84, And then they started appearing in a more geometric context around the early 2000s, in a work by Eisenbach-Schreier and also a work by Beauville. And in this work by Eisenbach and Schreier, they actually gave us a characterization of Ulrich bundles. And now we'll see what I mean by that. So just take an initialized coherent sheaf on a smooth variety X. And by initialized, I just mean that the vector bundle has global sections, but when you twist it back by -h, you don't have any section. Then you have that the following are equivalent. The first one is that the vector bundle is Ulrich, or the coherent sheaf is Ulrich. The second one is that the coherent sheaf admits a linear resolution over the ambient space. So we're considering a variety X embedded in a projective space. And here we have a resolution over the projective space. And this resolution is linear. It's linear in the sense that if you consider the map here, they can be represented by matrices of linear forms. So degree 1 homogeneous polynomials. And actually the exponents in the resolution just depends on the degree, on the rank. So here you see we have the generators. So the first one is the degree times the rank. And then the other numbers depend on the dimension and the degree and the rank. So you can compute all of them. The third condition, which is really useful and will be the one that we will use to check whether a vector bundle is Ulrich or not, is just given by certain vanishing in cohomology. So the thing that I want to say is that if you have a variety of dimension X, you need 2n vanishings to obtain an Ulrich bundle. So in case of surfaces, we just need 4 vanishings. And actually these vanishings imply that you have a lot of vanishings, not only these 4 in the case of surfaces, but we will see in the particular case of Hirzebruch surfaces, what is the cohomology table of an Ulrich bundle. And the last one is that for some finite linear projection, then the direct image of the sheaf is trivial. So just one comment on the second point. Keep in mind the second point, so the characterization of the Ulrich bundles in terms of resolutions, because when I will describe Ulrich bundles on the Hirzebruch surface, I will make some comments on this resolution. But now, so we have the definitions, but actually Ulrich bundle carry many interesting properties. The first one is that they're both mu semi-stable and semi-stable. So mu semi-stable, I'm considering the semi-stability with respect to the slope. And the slope is defined to be the degree of the first Chern class divided by the rank. And by semi-stable, I mean that every subsheaf has a smaller slope than the vector bundle that you're considering. And the other stability condition is the Gieseker one, so it's with respect to the reduced Hilbert polynomial. And actually, Ulrich bundles have this nice property that they are mu stable if and only if they're stable. So the two notions of stability coincides. Another interesting fact is that they are zero regular in sense of Castelnuovo-Mumford, and they are globally generated. So they're generated by global sections. Another important property that I will heavily use during this talk is that they behave well with respect to extensions and direct sum. And by that I mean that if you have 2 Ulrich bundles, you take extensions, you land on an Ulrich bundle. And also if an Ulrich bundle can be decomposed as a direct sum of some vector bundles, they're also Ulrich. So we have this nice behavior. And as I told you in the first slide, they're ACM. And in some sense, they can be considered as the simplest bundle from the cohomological point of view. as soon as we describe the cohomology table of Ulrich bundle on Hirzebruch surface, you'll get what I mean by this point. And in the same paper by Eisenbach and Schreier, they raised two famous questions in this context. And the question is every variety the support of an Ulrich sheaf? And if so, what is the smallest possible rank? So we don't have a general answer to these questions. We know that if you consider curves, curves admit Ulrich line bundles, but as soon as you make a step forward, so you increase the dimension and you consider surfaces, you don't have a general answer to these questions. Although there are a lot of scattered results, I would say. And also, you have some results in higher dimension, and for some particular kind of varieties like hypersurfaces of PN. So if you consider an hypersurface in PN, it supports Ulrich bundles, but it's really hard to understand which is the smallest possible rank. So in that case, the hard part of these questions is the second one. But as you saw from the title, I will be considering a particular families of surfaces, which are the Hirzebruch surfaces. Let me just recall the definition to fix the notation. An Hirzebruch surface is a root surface over P1, and it has a nice description in terms of projectivized bundle. So if you take an integer, a positive integer E, then every Hirzebruch surface is isomorphic to the projectivize of the vector bundle OP1 direct sum OP1 minus E. You have a projection over P1. And in this talk, we just denote the Hirzebruch surface by XE. The Picard group is generated by a fiber F, a fiber of the morphisms, and a section C0. And you have the intersection relations given by C0 square equals minus E, C0F equal 1, and F square, which forms the ruling of lines of the surface, equals 0. To fix the notation, just if we have a divisor on the Hirzebruch surface, we will write the associated line bundles as O of A, comma B, or just AC0 plus BF. So we will use these two notations. So what is our goal? Our goal is to characterize Ulrich bundle on XE. Why characterize? Well, a standard approach in the study of Ulrich bundles is to find the answer to the question that I raised before. So is to understand whether a projective variety supports Ulrich bundle. And the way to do that is typically to try and construct them. So you try to construct Ulrich line bundles, which are, let's say, are not that common. And then you try to construct rank two Ulrich bundles. So it's you try to show that the variety supports this vector bundle by constructing them. So today I want to do something a little bit different because in the case of Hirzebruch surfaces, we already know something about the existence of Ulrich bundles. And in particular, there's a work by Aprodukost and Miroroj, in which actually they consider it a more general case of root surfaces over a curve of genus G. And they proved that this surface supports Ulrich line bundles with respect to this very ample line bundle, if and only if the first coefficient of the polarization is equal to 1. In this case, this is the only case. These are the only cases where the variety supports Ulrich line bundle, and we have exactly 2 Ulrich line bundles. And as soon as you consider the rank 2 case, then if A equal 1, then there exists a family of indecomposable simple, strictly semi-stable. Special means that the first rank class is fixed and is 3H plus K, Ulrich bundles. And every rank 2 Ulrich bundle is given by an extension of the 2-line bundles. So you only have strictly semi-stable Ulrich bundles. And if A is different from 1, then under mild assumption of the polarization, but we can forget about this because in the case of Hirzebruch's surfaces is automatically satisfied. Then the surface supports rank 2 special stable Ulrich bundle. So in this case, you have stability, and that's because you don't have Ulrich line bundles. So as soon as you construct a rank 2, Ulrich bundle is automatically stable. So as you can see, we have some existence results, and also the answer to the minimal rank is settled, because in one case you have Ulrich line bundle, in the other case you have rank 2 Ulrich bundles. But we have some restrictions here. The first restriction is that we are considering Ulrich bundle with only one possible first rank class. So as soon as you have an Ulrich bundle, you have that the degree of the first rank class is fixed. But when the Picard group is not isomorphic to Z, then you can have more than one admissible first rank class. In this case, the existence is settled only for one case. So the special case, the case where C1 is 3H plus K. But we would like to consider every admissible first rank class and also every possible rank. And the other thing that I want to do is to try to describe them. And by describe them, I mean to find a resolution of an Ulrich bundle, but this time not on the ambient space, but on the variety itself. And in order to do so, I will need a bit of the derived category of sheaves that were introduced in the previous talk, but I will just give you the really basic definitions and idea. So if you consider this derived category of Korean sheaves, then an object is called exceptional if the OM inside the derived category of sheaves is a one-dimensional algebra generated by the identity. And when you have an ordered collection, as you saw before, this is called an exceptional collection if there's no map, no OM or any X from, let's say, right to left. Actually, there's another condition which is being strongly exceptional, and in this case, you also require that there's no X from left to right. So you can have some homomorphisms from left to right, but no higher X. And an ordered collection is said to be full if it generates the bounded category of sheaves.
So your objects are exceptional here.
What?
The objects.
I'm sorry, I didn't understand. Yes.
The objects of the collection.
Yes, okay. Yes, they're exceptional. Yes. So the idea is to apply a Bayesian type theorem. I was lucky that in the previous talk, it was stated the original version of the Bayesian theorem, the one of the projective space. But actually, you can do something on other varieties if you have the additional property that the collection that you're considering is a fully strong exceptional collection of locally free sheaves. And that's the case for Hirzebruch surfaces. And in this case, let me state the theorem. So if you have this collection, this nice, I'll say nice because it's a bit rare to have these kind of collections, but in this scenario, then every coherent sheaf of the variety can be described in terms of a complex. So you have a complex of vector bundles, which is exact everywhere except in degree 0. And the cohomology of this vector of this complex of vector bundles is exactly the coherent shift that you're considering. Each term, as you can see here, is just a certain number of copies of the elements of the exceptional collection. So a direct sum of a number of copies of the elements of the collections. So if you don't have this nice additional property on the collection, you're not able to obtain a complex, but you have a spectral sequence which degenerates to the coherent shift that you're considering. So as you saw from the Beilinson type theorem, this kind of approach is really helpful when you consider vector bundles with few non-vanishing cohomology groups. And as you recall, I told you that Ulrich bundles are vector bundles with the simplest possible cohomology. So let's see what I meant by that. If you consider an Ulrich bundle of rank R, so any rank on the Hirzebruch surface, then the first thing that you can say is that when T and S are in this range, so AB is the polarization, then you only have the H1 of the vector bundle, which can be different from 0. Instead, when T and S are big enough, you only have H0. This is not surprising, but that's the actual range. And of course, by duality, you have a similar result about the H2. So for TNS small enough, negative enough, let's say, you only have that the H2 can be different from 0. And we will say that the vector bundle ETS has natural cohomology for such TNS. Natural cohomology just simply means that there exists at most one cohomology group that is different from 0, which has dimension different from 0. Okay, so a few comments here. The first one is that this is a nice description of the cohomological table of an Ulrich bundle, but it's not a complete one. So if you consider TNS to be really unbalanced, so for example, one very positive and the other very negative, well, actually, you cannot say anything about the cohomology of the Ulrich bundle. In particular, if you don't have additional conditions on the Ulrich bundle, I think it's impossible to obtain a complete result. And when we'll talk about stable Ulrich bundles, I will say something about that. But now we have all the ingredients to state one of the theorem of this talk. So if you consider a polarized Hirzebruch surface, and you consider a rank R Ulrich bundle with fixed C1, so you have the C1 which is given by alpha C0 plus beta F, then the vector bundle fits into this short exact sequence. So in particular, we have this resolution of an Ulrich bundle, and the exponent this time only depends on the first chain class, the rank, and the polarization. So actually, okay, let me finish the theorem and then I'll make some comments. You also have a short exact sequence when the vector bundle is realized as the kernel of a certain map, which is similar to the first one, but this time you have the Ulrich bundle realized as kernel and not as co-kernel. So you recall that in one of the first slides, in the definition of an Ulrich bundle, I told you that an Ulrich bundle is a vector bundle that admits a linear resolution over the projective space. So here we have a resolution. Is it really that different? Well, Yes and no. Yes, because it has the really stronger property to be a resolution on the variety itself. So it's not a resolution over the ambient space, but it's a resolution on the variety. The other feature of the resolution was to be linear. Well, in this case, the resolution is not linear, but it's not far from linear. Just consider the simplest case when E is equal to 0. So you have P1 cross P1. In this case, if you put E equals 0, then you see that the first map in this short exact sequence can be represented as a two-block matrix. And each block is made of homogeneous form in the variable of 1p1. So it's like a matrices of bi-homogeneous form or by degree 1, 1. So it's not that far from being linear. But in this case, you have this other description. So now there's a natural question. We saw that as soon as we have an Ulrich bundle, we can describe it in terms of a resolution. But what about the converse? So if you take an injective map between the vector bundles here, these two vector bundles, is it true that the co-kernel is Ulrich? Well, we need some more condition. So if you take an injective map with the right exponents, so the right invariants there, if the degree of the first Chern class is the right one, so as I told you before, the degree of the first Chern class of an Ulrich bundle is fixed and is exactly equal to this number, then the co-kernel is an Ulrich bundle if and only if satisfy this vanishing in cohomology. So the H2 of E minus 2H is equal to 0. And another an analogous result also for the other resolution. So when you have the kernel, you have a similar result. So on these two theorems, are there any questions? Oh, okay. So if you have any questions, just stop me at any point. So let's see some consequence for these two theorems. The first one is that the existence of an injective map is always guaranteed. So we can always have an injective map to hope to have Ulrich bundles. So that's the first point. The second point is that if you consider the short exact sequence with the two vector bundles and the co-kernel of the map, the injective map phi, then just taking the cohomology, you see that you have these two vanishings in cohomology. And these are two of the four vanishing that you need for an Ulrich bundle. The other two are the H1 and the H2 of E minus 2H. So we only need two vanishings at each point. And what happens is that if you twist the short exact sequence by minus 2H and you take the cohomology, you have this scenario. So you have the two cohomology groups that you want to kill in some sense. And then you have this map here between these two cohomology groups. And actually, these two cohomology groups have the same dimension. So basically, what happens is that as soon as one of the two cohomology group, H1 or H2 is 0, then also the other is 0. And that gives you the how to obtain an Ulrich bundle starting from a map. So you need to check this vanishing. Okay, let's say something more, because another important point is that the non-negativity of the exponents in the resolution imposes some condition on the first chain class and on the rank. So let's say that you fix the Hirzebruch surface and you fix the polarization, then the exponents only depend on the first chain class and on the rank. And as soon as you put them to be non-negative, you obtain some conditions. In a special case, special, it's a bit tricky word, but in the case of special Ulrich bundles, so rank 2 Ulrich bundles where the first chain class is 3H plus K, so the one case in which we already know the existence, then it's possible to prove that the condition on the H2 is always satisfied. So basically you obtain an alternative proof of the existence and also as some kind of description of their moduli space, because you just you can take the space of matrices represented by the map phi, take the open subset of injective maps, and you have to quotient by some automorphism of the variety, but you can have a description of the moduli space. Moreover, now the obvious question is, can we say something in the other cases? So when the rank is greater than 2 or when the C1 is different from the special one? And actually, using a result by Koskun and Wizenga, it's possible to show that if you take general map phi, then the vanishing H2 of E minus 2H is, you obtain this vanishing because you obtain that the co-kernel of this map has natural cohomology. In particular, the H1 and the H2 are equal to each other. If it has natural cohomology and you also know that the Euler characteristic is equal to 0, then they must be both equal to 0. And in particular, this, as a consequence of this strategy, we will have the second theorem, and that is the fact that every Hirzebruch surface for any polarization admits Ulrich bundles for any admissible rank and any admissible first chain class. So here I'm cheating a little bit because I didn't told you what an admissible rank and admissible first chain class is. Of course, you can imagine it, but we can be a little bit more precise with this concept. But before doing that, I will make a last comment on these two theorems. So here we saw in the previous slide that in the case of special Ulrich bundle, the condition on the H2 is always satisfied. Also, if you take the general map, the condition is satisfied. So one can ask, well, maybe we don't need this condition. Maybe it holds for every injective map phi. Well, actually, that's not the case. That's not the case. You can construct counterexamples. The easiest way to do so is just to consider vector bundles over P1 and pull them back over the variety with the right invariance. You can combine them. You obtain something that fits into the resolution, but it's not Ulrich. So that's one way to construct counterexamples. But you can do something better. You can actually describe the locus of non-Ulrich bundle inside the space of matrices. And here I will just make an easy example. So if you take P1 cross P1 embedded as a del pezzo surface, so anti-canonically, then on this variety, you can consider rank 2 Ulrich bundle with the C1 equal 3 C0 plus 5F. This is not the special one because the special one would be 4 C0 plus 4F. So it's another admissible first chain class. And in this case, you can consider rank 2 vector bundle described as the co-kernel of this injective map. So when we saw the resolution, I told you that it's not linear, but it's not far from linear. And in this case of P1 cross P1, you can easily see this thing. In fact, here the y0, y1 are the coordinates of the, let's say, first P1, and then you have the coordinates of the second P1, y2 and y3. You see, these are just homogeneous forms in these variables. So this is the associated matrix. And actually, with a little bit of effort, you can build this big matrix, big square matrix B. And the non-Ulrich locus is given by the determinant of this, the vanishing of the determinant of this matrix. So here, the betas are just the coefficient of the matrix representing phi. In particular, you have this description of the non-Ulrich locus as a divisor inside the open subset of the space of matrices, which represent injective maps. As soon as you consider other varieties or higher rank Ulrich bundles, the computation are a little bit more tedious, let's say. But in this easy case, you have this nice example. Okay, so now I can focus on what I meant by admissible rank and admissible first Chern class. So let's try to give this new definition. Let's start with a rank R vector bundle E with a fixed first Chern class. In this case, we say that the pair RC1, so the pair rank and first Chern class, is an admissible Ulrich pair with respect to H, if and only if the C1 has the right degree. So that's the first condition. And the other condition is that the first Chern class actually satisfies the numerical condition imposed by the resolution, which can be written in this way. So we have a certain range for alpha and beta, and we have strict inequalities if E is greater than 0 and A is greater than 1. And that's because it's related to the fact that in these cases, we don't have Ulrich line bundles. Obviously, now I'm about to say something really silly, but let's just say it. From the definition, it follows that RD is not an admissible Ulrich pair, then there cannot exist a rank R Ulrich bundle with that fixed C1. So that's the idea of an admissible Ulrich pair, as you can imagine. Okay, so now we have this definition. Let's try to apply it to some concrete cases. Let's try with the first easy case, the rank 2 case. So when we consider a rank 2 Ulrich bundle of on an Hirzebruch surface, then the admissible Ulrich pair, in this case, I'll say admissible first Chern classes because I'm fixing the rank to be 2, are given by these divisors. So we have this description. K is an integer in this range, and if you look at the range of K, you see that the greatest common divisor between A and B, it's in some sense a measure on the possible admissible first Chern classes. So if this greatest common divisor is big, you will expect a large number of admissible first Chern classes. Otherwise, you have the extremal case that if the greatest common divisor between A and B is equal to 1, then the only possibility for the first Chern class of a stable rank 2 Ulrich bundle is the special one. So you only have the special. And if you take A to be 1, then you have two more admissible first Chern classes. So you have the special one and the other two admissible first Chern classes, and they correspond to the extension of the Ulrich line bundles, the trivial extension. Just take a line bundle, 2 copies of the same Ulrich line bundle. So in some sense, the polarization with the greatest divisor between A and B equal to 1 gives us the least possible number of the admissible first-channel classes. So that completes the picture for the rank 2 case, but what about higher rank cases? Well, for higher rank, it's harder to explicitly compute the admissible Ulrich pairs. We will say something, but in that cases, we will need some additional hypothesis. Otherwise, it's basically impossible to explicitly write in the full generality the admissible first-channel classes. But so now, why do we need these admissible first-channel classes? Because if you think at the second theorem, we know the existence of this kind of vector bundles. So one may ask, why do we need to, keep on investigating them? Well, the point is that you know the existence, but you don't know anything about the indecomposability of these vector bundles. So basically, you would like to study and try to prove the existence of stable Ulrich bundles, and stable would imply indecomposable. And in the rank 2 case, here we have some results about the moduli space of rank 2 stable. So in this case, this is the moduli space of stable vector bundles with fixed invariants with respect to polarization H. And here I just want to say that this condition on the C2 is to ensure the non-emptiness of the space. And the condition, so here is for rational surfaces. If you take Hirzebruch surfaces, you have this condition on the polarization. The condition on the second channel class is to ensure the non-emptiness. And actually, the moduli space of stable rank Ulrich bundles with fixed determinant and a fixed second channel class is an open subset on the, of this moduli space of stable vector bundle with this invariant. And we will just denote by mu. So if you consider the space of stable Ulrich bundles, then you see that when you consider an Hirzebruch surface with A equal 1, then the moduli space of stable Ulrich bundle is empty for R greater or equal than 2. So it means that you only have strictly semi-stable Ulrich bundles, which are extension of the Ulrich line bundles. So now the question is, for which admissible Ulrich pair is the space of stable Ulrich bundle non-empty? Can we say something? Well, actually, we can say there are some, let's say, easy cases. And they are the case of Ulrich bundle of rank 2 and rank 3. And why is that? Well, the main thing that you have to keep in mind is that an Ulrich bundle can only be destabilized over another Ulrich bundle. And the co-kernel of this inclusion map that you have will be also Ulrich. So what happens when you consider the rank to be 2 or 3? In this case, the existence of strictly semi-stable Ulrich bundle would imply the existence of Ulrich line bundles, because it can only destabilize over an Ulrich line bundle. And we know that if we take E to be greater than 0 and A to be greater than 1, so in this with these two hypotheses, then what happens is that the variety does not support Ulrich line bundles. In this case, using the theorem that states the existence of Ulrich bundle for any admissible Ulrich pair, then you have that these vector bundles are automatically stable. And also, the open subspace MU is multi-reducible, unirational, and it's a quasi-projective variety because it's an open subset in there. And you can compute the dimension using the classical strategy of computing the X1 of E inside itself. So that's the first existence result about stable Ulrich bundles of rank greater than 2. So also we have the existence of a stable Ulrich bundle of rank 3. And this holds for any admissible Ulrich pair. So we saw for the rank 2 case, which are the admissible Ulrich pairs. For the rank 3, there's a similar description. And so basically here, the free point of considering the rank 2 and 3 case is to have the non-emptiness of this space. In this theorem, I've considered Hirzebruch surface with the invariant E greater than 0. A quick comment on what happens when you consider P1 cross P1, which is in P1 cross P1, the main obstacle is that it always admits Ulrich-Klein bundles for every polarization. So not just when A is equal 1, but for every polarization. And in this case, it is possible to prove the existence of stable rank 2 Ulrich bundles. But you cannot use directly the previous theorem to obtain the existence of stable ones, because in principle the family of strictly semi-stable vector bundles can cover all the moduli space. So in particular, you need some other strategies, and one of the strategies can be to construct rank 2 Ulrich bundles using the Kelly-Bacharach constructions. So the relation between two codimensional subscheme and vector bundles over surfaces. And using that correspondence, you're able to construct stable rank 2 Ulrich bundles. So actually, you can do that. And also, there's another way to construct Ulrich bundles, but I will tell you about it in the end. Now, in the last part of the talk, I would like to focus on the higher rank cases. So here, the main problem is to determine which are the admissible Ulrich pairs. This is the first problem. And actually, in order to have some, let's say, reasonable result, you need some more assumptions. And the first one is about the greatest common divisor. So you want the greatest common divisor to be equal to 1, because in this case, as we saw for the rank 2 case, you expect the least possible numbers of admissible Ulrich pairs. So that's the first hypothesis. The second hypothesis about E and A are to exclude the case where the variety supports Ulrich-Klein bundles, which can be a little bit tricky. And the last condition is just technical. It's just technical to be able to express the admissible Ulrich pair in as I told you, in a reasonable way. So with these three conditions, then the admissible first-order classes are given by this formula, and where k is an integer in which varies in this range. And the range only depends on the rank and the polarization. Okay, so now there's a nice behavior. Let me fix this invariant. This invariant delta t to be t times b over b minus ei plus e. It may seem a little strange, and one can ask, where does it come from? Well, it comes from this observation. Let's say, The observation is that the K lives in this range, no, between R plus that coefficient and 2R minus that coefficient. Well, so one can ask, are there some values of the polarization of the rank where there's no integer in that interval? Well, actually, using this invariant, one can say that in the same hypothesis of the previous proposition, then if R is smaller than delta 1, there are no admissible Ulrich pair with R odd. So one is able to exclude something. And so that's the role of delta 1. What about the other deltas? So what happens when R is between delta 1 and delta 2? Well, in this case, if R is even, then the only admissible Ulrich pair is given by the, let's say, the special one. Because if the rank is 2, you just obtain the special Ulrich bundle. If the rank is different than 2, you obtain something that can be considered as a generalized special, let's say. So this is for when R is even. When R is odd, in this case, you have exactly 2 admissible Ulrich pairs given by the special one minus a correction term, minus a plus a correction term, and this correction term is given by this divisor. And actually, you can start to see a pattern, and the general idea is this one. If R is between delta t minus 1 and delta t, then you have at each step an increased number of admissible Ulrich pairs. And here I've divided by the parity of R. And the last observation is that there's an upper bound. There's an upper bound on the admissible Ulrich pairs because one can easily prove that R is smaller than delta R. And so the maximal number of admissible Ulrich pair is given by R minus 1 at each step with this hypothesis. Okay, so now we are ready to state the final results that I want to present to you. The first thing is that if you consider the Hirzebruch surface with this kind of strange hypothesis, additional hypothesis, then the Ulrich pair R, let's say the generalized special Ulrich pair, is always admissible. So in any case, it does not depend on delta 1 and the other deltas. It's always admissible. And because of this, we're able to prove the last results that for any even rank smaller than delta 1, there exists a stable rank R Ulrich bundle E with that fixed first rank class. Let me give you just an idea of the proof. The idea of the proof is a dimensional count of the strictly semi-stable Ulrich bundles. So the first thing that you want to use is that if you take a now split extension of 2 non-isomorphic mu-stable bundles with the same slope, you obtain a simple vector bundle. So you start by taking an extension of 2 special Ulrich bundles, so rank 2 special Ulrich bundles. The existence is settled by the previous theorems. And you obtain something of rank 4. By induction, you can construct a simple Ulrich bundle of arbitrarily high rank. Then you consider the modular family of simple bundles with these fixed invariants. And you show that the dimension of each family of strictly semi-stable Ulrich bundles, which is realized as an extension of stable bundles, is smaller than the dimension of the modular family. So in particular, you see that through this dimensional count, you're able to prove the existence of stable Ulrich bundles. So that's the idea of the proof. Why do we need the delimitation on the delta one? Because I told you that the admissible Ulrich pair R and the special C1 is always admissible. Well, using the result of the previous slides, on the previous slides, this condition now R smaller than delta one implies the non-existence of odd rank Ulrich bundles. So in particular, this gives us less ways in which the strictly semi-stable Ulrich bundle can decompose. And otherwise can be a bit overwhelming, all the ways that the Ulrich bundle can decompose. Okay. And okay, so that's the first thing. And the other thing is that if you drop the hypothesis on the polarization, you're not able to have a clear picture of all the admissible Ulrich pairs. So you know that the special one is admissible, but then you don't have control on the others. So the vector bundle can split in some strange ways, and you're not able to control it. So we need this additional hypothesis to be able to say something about stable and thus indecomposable Ulrich bundle of higher rank. The last thing is that one may think that the hypotheses are smaller than delta one is a bit, can be a bit restrictive in the sense that it only holds for some ranks. But actually, what I want you to notice is that delta one does not have an upper bound. So you can choose particular polarization and obtain an arbitrarily high delta one. So it's not like delta one can be at most 10, so you have the existence up to rank 8. Delta one can be really high. So I think that I will stop here. So thank you very much for the attention.
Thank you, Vincenzo. So any questions?
Do you have any kind of compactification of the some moduli spaces? Ulrich?
Well, at this point, I don't know, but I think one important tool will be to use the resolution, because let me go to the resolution, and here. Okay, so let's say here you have the space of matrices. You take the open subset of the one representing injective maps, and for example, this gives you the unirationality. So all the, let's say, non-trivial information about the moduli spaces are obtained using this resolution. So maybe you can. I mean, it would be the first thing that comes to mind, to use this resolution to obtain some compactification, but at this point, I don't know.
Thank you.
Go ahead, Alexander, you have a question.
I would like to ask, are there any cases when the moduli space of Ulrich bundles is an open subset of the ambient component of moduli of bundles on this given surface XE?
So in the rank 2 and 3 case, you know that the moduli space. I mean, there are some results about the reducibility of the moduli space of the coherent of the semi-stable vector bundles. So I'm not talking about Ulrich. So in this case, you have this open subset in the only component. In the other cases, I don't know. I don't know even if the moduli space is irreducible. For rank 2 and 3, it's true.
I
For
see.
higher rank, I don't know.
I see. Thank you. Thank you.
So I have a question as well. Vincenzo, if you go to your slide 20, please.
Okay, slide 20.
Related to Alexander's question, in this proposition,
Yes.
you say that the moduli of Ulrich bundles smooth, reducible, irrational, and this is an open subset in the moduli space of all bundles or all sheaves with these Chern classes. Is
Yes.
that correct?
Or stable one with that classes. Yes.
So
In
do you have
the rank?
Yeah.
Yes. So sorry. Yeah.
Do you know what happens in the boundary, so to speak? Are there things that are locally free? Is there such a thing as a non-locally free Ulrich sheaf?
Non locally free, no, because that's because the as soon as you consider an Ulrich sheaf, in this case over a smooth surface, it will be automatically locally free. The condition Ulrich implies the fact that it will be locally free. I don't know if there's what is it at the boundary that I don't know, but for what concerns locally free, it's being Ulrich gives you the locally freeness, let's say.
Okay, thank you.
Okay.
Yeah, so this is perhaps one way to compactify the moduli space of Ulrich bundles. Like
Yes.
Looking at this moduli space of stable sheaves.
Yeah, sure. My question was whether there are a sort of minimal compactification. Maybe this one is very big.
Oh, okay.
More questions? Anyone?
Sorry, I have a question. So for the odd rank case, they don't exist for delta 1, for R
For
less than delta 1, or anyone?
Yes.
Okay,
No,
so
R
just
less than delta 1. Yes, and
Okay.
that's because if you have this condition, this ensure you. I mean, this gives you that there's no integer in this range, so you have some numerical obstruction to have an admissible Ulrich pair.
Okay.
But
And
as soon
for
as you,
higher T, did you check or you have examples for?
No, I didn't check. I have examples of Ulrich bundles, and one way to construct them is to use the resolution. You can use Macaulay too. You can use a software, because, as I told you, this resolution is kind of nice in terms of the map of the map involved, and you basically can construct a vector band, a sheaf using Macaulay 2. Just take the matrix representing the map phi. You sheafify the co-kernel and you check that it's Ulrich. And with Macaulay 2, if you take a random matrix of the right dimension, right blocks, etc., you will obtain an Ulrich bundle. The problem, the big problem, is to show that that it's stable. Because if you take, let's say, a rank 10 Ulrich bundle, then it can be destabilized in a big number of ways, by rank 2, rank 5, rank 4, and rank 6, rank 1, rank 9, and so on. So you have to check the dimension of each family, and can be a little bit problematic. Also because there are a big number of admissible Chern classes at each set.
Okay.
So for odd rank, I don't have an example of a stable Ulrich bundle, but if I have to guess, there exist.
Okay, thank you. So thank you. So let's thank the speaker